AI, ML, LLMs, data models, data engineering. These buzzwords are everywhere. Every career guru seems to push you towards pouring your money into startups, flaunting these terms into crypto trading platforms that claim to harness them for maximum profitability. And that is not my world. I don't chase that hype. I build what the mainstream media cannot even begin to put into words. I work in the unseen, unknown, and often undiscovered domain of capital equipment, the physical backbone that makes all this digital magic around you possible. While many others will talk about a digital future, I focus on the machines that make that future possible. Digital Trends, the news outlet, they recently published an article about me and this podcast. So please feel free to Google that one or, look at the link below in this description of this video. In today's episode, we're diving deep into the hardware interfaces that power the transmission of data, the silent enablers behind the rise of data models, LLMs, and AI. We will peel back the digital curtain to reveal the physical machinery that actually makes it all possible. This isn't just about tech, it's about how the 21st century world actually spins. We will even talk about what's going on in the space front, how NASA, ISRO, Indian Space Research Organization, or ESA, which is the European Space Agency, and other space agencies are working towards preparing their satellite infrastructure up in the literal space, ready to handle the petabytes of data for tomorrow's digitalization of every aspect of our lives. Welcome. As is the name of the podcast, we start with thinking about a problem or opportunity, which is the first episode for any topic. Then we build the product in the second episode. And on the third episode, we talk about how to scale a company using that product. We repeat the sequence of the nature of the episodes for all the topics that will be talked about in this podcast. This is the first episode for the topic of a conceptual and yet very well possible satellite. A satellite that uses lasers for data transmission, which finally enables our growing needs for data models, AI, ML, LLM, and whatnot. Before I proceed, I want to make you aware that no NDA has ever been violated while making any of the episodes of my podcast, and today is no different. So stay tuned. On the left of your slide here, you see a typical data journey from data creation through ingestion, transmission, storage, and then all the way to compute, training, and then finally deployment of data. But as is my brand, I always talk about the hidden aspects of technology, the knowledge that is generally unspoken due to its complexity and therefore not very appealing to masses. Today, we're going to talk about satellites. Satellites have a critical role in every single one of these data creation to data deployment steps. You have data creation, you ingest, you transmit, you store, compute, train, and then finally deploy. So throughout making any of these data models, satellites really play a big role. Satellites generate vast streams of raw data via remote sensing, GPS, and scientific instruments. Modern satellites don't just send raw data anymore. They filter, compress, and even run edge interference on board before transmitting anything down. With optical interlinks and laser downlinks, they are the backbone of global data movement, especially in areas where fiber, optics, or 5G can't reach. Storage. They enable inputs into hybrid data lakes, and some architectures even treat satellites as part of resilient, disaster-proof archival systems. Think of satellites as the missing link between edge and cloud, connecting remote or underserved areas to high-performance compute. Many data sets, especially for environmental, agricultural, or climate models, are either created or enriched using satellite imagery. Satellites can deliver models and AI apps to edge devices in isolated zones, closing the loop where traditional networks all fall short. And finally, they're vital for real world validation and continuous data refresh cycles. So, in a sense, when we think of training and deploying powerful models, especially in the age of LLMs and the autonomous systems, satellites are no longer just passive data collectors. They are integrated, intelligent infrastructure components. This is why this episode and the upcoming 2 episodes will be dedicated to satellites and the major plans behind different governments for their satellite and space objectives. How would you benefit? Try to think of how your organization can act as a supplier towards the different space agencies of different countries. We will talk more about it in our second episode as well as the third episode of the series. Space agencies are not just launching satellites, but also preparing infrastructure for AI and large language models. Yes, the same tools powering your smart assistants and research platforms are now getting support from orbital level innovation. Let's start with NASA. They have teamed up with IBM to build the Indus LLM suite, which is tailored specifically for earth science and astrophysics. Instead of relying on generic data, it's trained on curated scientific literature. So we're talking domain-specific intelligence here. They're also behind the Geospatial AI Foundation model, using satellite data to help with everything from agriculture to disaster prediction. It's open source, which is fantastic for the global research community. Now we go over to ESA, the European Space Agency. European Space Agency is taking a double-pronged approach. Internally, they have developed ASK-ESA, a self-hosted LLM, to enhance knowledge management within the agency. Imagine a really smart internal assistant that knows space operations inside and out. And then there is more futuristic angle, using LLM-based systems to train autonomous agents for planetary landings. That is not just science fiction. That's mission automation in real time. We will talk a lot more about ESA, where I will explain how ESA is planning to launch a very specific mission called Hydron. And we will actually, in this episode and the upcoming 2 episodes, we will talk about a hypothetical satellite that will enable that project, that mission. All right, let's continue with talking about the different space agencies around the world. ISRO in India, which is International Indian Space Research Organization, is making moves with an eye on digital independence. They're investing in foundational LLMs and localized data strategies as a part of their AI sovereignty initiative. That means they're not just using AI, they're building it on their own terms. Adding to that is their RESPOND program, RESPOND, which investigates practical AI use cases like anomaly detection in system logs. The UAE Space Agency is moving fast and with scale. Through the Technology Innovation Institute, they launched the Falcon LLM series, a powerful suite of open source models that's already outperforming some big name competitors. And it's not just code. They're putting serious capital behind this with a 100 billion MGX fund investing in AI companies globally to position the UAE as a key player in the AI economy. Iran has entered the game as well, and they have committed $100 to AI research and then launching their own national AI platform prototype. Their aim to lead the Middle East in AI infrastructure, both on Earth and in orbit. And last but not the least, our neighbors from the down under, Australia. They have supported startups like Spiral Blue, which developed the SE1, the most powerful AI edge computer in space outside of a station. It's a huge leap for autonomous in-orbit processing, minimizing the need to send all that data back to Earth first. Infrastructure for AI is going interplanetary, and it's not just about data science. It's about every nation's sovereignty and yet on how each nation maintain collaborative trade relationships with each other. The idea behind this podcast is always to give the audience an understanding of how boardroom discussions are made and how detailed decisions on design, suppliers, manufacturability, etc. are made. And then finally, again, on how the boardroom discussions are made on scaling that product or the company. I generally talk from three perspectives: a startup, a scale-up, and an established organization. But for something like a space project, it seems safe to assume that an established organization would embark on a project pertaining to satellites or applying satellites for space exploration in general. So look at this slide in front of you. Hydron is imagined as a space-based extension of Earth's fiber optic infrastructure, capable of terabyte per second throughput and operating across all satellite orbits, the LEO, MEO, and then GEO. ESA's intention is not incremental improvement, but a paradigm shift from radio frequency to optical networking, resulting in a seamless, high-capacity global communication layer. But there is a catch. There are no real optical fibers. Instead of guiding light through glass cores, as is in terrestrial optical fibers, Hydron guides data via laser beams through space. These beams maintain coherence and directionality over long distances, acting like invincible, high-speed fiber strands connecting nodes in orbit. The Hydron High Throughput Optical Network project, spearheaded by European Space Agency, is a groundbreaking initiative aimed at revolutionizing satellite communications through the development of an all-optical multi-orbit network. This network is designed to deliver terabyte per second data transfer capabilities, effectively extending terrestrial fiber optic networks into space, a concept often referred to as fiber in the sky. Common objectives of Hydron. Number one is the demonstration of an all-optical multi-orbit network. Hydron seeks to establish a seamless optical communication network that operates across various orbital layers, including the low Earth orbit, LEO, medium Earth orbit, MEO, and geostationary orbit, GEO. This network aims to provide high-capacity data transport and flexible connectivity for both space-based assets and ground users. Number two would be integration with terrestrial networks. A key goal is to ensure that the space-based optical network integrates seamlessly with existing terrestrial fiber optic infrastructure. This integration is crucial for achieving low latency, high throughput data transmission, thereby enhancing global connectivity. Number three would be validation of advanced optical technologies. Hydron aims to validate critical optical communication technologies such as high data rate wavelength division multiplexing, which is WDM they call it, and then inter-satellite links and onboard optical routing or switching mechanisms. These technologies are essential for the efficient operation of the envisioned high-capacity network. Support for future communications and missions. By demonstrating the feasibility and advantages of optical communication in space, Hydron will lay the groundwork for future institutional and commercial telecommunications missions that require advanced next-generation communication capabilities. Hydron Demonstration System, or Hydron DS. To achieve its objectives, ESA is implementing the Hydron Demonstration System, which involves the development deployment, and in-orbit testing of a scaled-down version of the full Hydron network. The Hydron DS is composed of the minimum number of elements, both in space and on ground, necessary to demonstrate high-capacity data transport and flexible network capabilities. So, of course, before the ESA goes and launches a full-scale project, they have to demonstrate that the concept works. So, Hydron DS or Hydron Demonstration System is nothing but a prototype. It's as simple as that. The Hydron DS has two mission objectives: technology verification and operational concept validation. This is nothing but a proof of concept, simple as that. Or you can also call it a minimum viable product. So technology verification, to validate the performance of the optical communication technologies in an end-to-end system demonstration, they need to verify that. And then operational concept validation would be to assess and refine operational concepts in support of service demonstrations, paving the way for future commercial exploitation. All right. Phased implementation. The Hydron project is structured into multiple phases. Phase A to B1. Phase A was initiated in 2022, and this phase involved two parallel competing contracts awarded to industrial teams led by Thales Alenia Space in Italy and Airbus Defence and Space in Germany. The focus was on consolidating potential technical baselines and associated programmatic and cost estimations. Phase B2, C, D, and E. This upcoming phase will involve close cooperation between the selected Hydron DS Industrial Consortium and ESA to further develop and implement the Hydron DS. Strategic importance. Hydron is part of ESA's optical and quantum communications. It aligns with the agencies. Hydron is a part of ESA's optical and quantum communications. This project aligns with the agency's broader goals to strengthen Europe's use of space and security, as outlined in the ESA's Agenda for 2025. By fostering innovation and collaboration among European and Canadian industries, Hydron aims to position Europe at the forefront of optical telecommunications. In summary, Hydron is a visionary project that seeks to transform satellite communications by leveraging optical technologies to create a high-capacity integrated space terrestrial network. Its successful implementation will not only enhance global connectivity, but also support a wide range of applications, from environmental monitoring to disaster response, and then it paves the way for future space missions, of course. Whenever there is a product that needs to be engineered, be it software or hardware, there is always some features that the board wants to see, or the final end users or the customers want to see. Satellites are no different. So there are three primary features sought for the final system of space-based optical communication network: multi-orbit connectivity, no dependence on radio frequencies, and then finally, high-capacity terminals for space and grounds. Multi-orbit interoperability. Hydron is designed to operate seamlessly across low Earth orbit, medium Earth orbit, and geostationary orbit. The project includes the development of a LEO, low Earth orbit satellite collector with advanced optical communication capabilities, building upon previous developments to evolve into a multi-layer system with terminals linking between LEO and GEO and the Earth. An RF-free architecture. A core objective of Hydron is to transition from traditional radio frequency communications to an all-optical network. This involves implementing high data rate optical feeder links, wavelength division multiplexing, optical intersatellite links, and onboard optical switching route capabilities, thereby eliminating reliance on RF systems. High-capacity optical terminals. Hydron aims to achieve terabit per second throughput with a minimum of 100 Gbps per link. This is facilitated by advanced optical terminals capable of supporting both inter-satellite links and satellite-to-ground optical connectivity, integrating seamlessly with Earth's existing fiber networks. The ESA specification for terabit per second optical links, ESTOL, outlines the technical standard for these high capacity terminal. All right. Integration with the terrestrial fiber network. The vision for Hydron is to create a fiber in the sky extending terrestrial fiber optic networks into space. This involves seamless integration of space and ground segments, enabling optical communication systems to become an inherent part for terrestrial high-capacity transport network. The ground segment of Hydron includes fixed and transportable optical ground stations developed by DLR IKN and Officia Stellar, respectively. These stations are integral for establishing high-speed optical feeder links between satellites and Earth, onboard optical switching and routing. Hydron incorporates onboard optical processing capabilities, including all optical or regenerative routing and switching of optical signals. This enables efficient data traffic redistribution, load balancing within satellite fleets, and flexible assignment of satellite payload resources. Machine learning for network optimization. The ML40C Machine Learning in Optical Communication System project explored the application of machine learning to optimize onboard laser communication terminals and traffic routing in optical networks. This includes improving spatial acquisition and network management, enhancing the overall availability and efficiency of the optical links in the Hydron project. These features collectively contribute to Hydron's goal of establishing a high-throughput all-optical communication network in space, integrating seamlessly with terrestrial networks and supporting future markets that demand ultra-low latency, high throughput, and secure global connectivity. How beautiful, right? Hydron's fiber in the sky concept. Hydron's fiber in the sky concept complements existing terrestrial fiber optic networks. This enhances global connectivity and addresses a lot of limitations that we face today in data transmission. These kind of limitations will be number one, extending connectivity to remote and underserved regions. So laying fiber optic cables in remote, rural, or oceanic regions is often economically not feasible and not logical, and logistically extremely challenging. So Hydron aims to provide high-throughput optical connectivity to areas lacking infrastructure, efficiently bridging the digital divide. By deploying satellites equipped with laser communication terminals, Hydron can deliver broadband services to regions where terrestrial networks are absent or unreliable. Another problem that Hydron is solving is reducing latency for time-sensitive applications. Terrestrial fiber networks, while fast, often follow indirect routes due to geographical and political constraints, resulting in increased latency. By establishing near straight-line optical links between satellites and ground stations, Hydron can significantly reduce data transmission latency. This is particularly beneficial for applications like high-frequency trading, autonomous vehicle coordination, and real-time remote operations where milliseconds really do matter. The third advantage is enhancing network security and reliance and resilience. Terrestrial networks are susceptible to physical disruptions and cyber threats. Space-based optical links are less prone to physical damage and offer inherent resistance to electromagnetic interference. Hydron's architecture includes multiple orbital layers, LEO, MEO, and GEO, providing redundant pathways for data transmission. Thereby, it enhances the overall network resilience. Number 4 is alleviating terrestrial network congestion. The exponential growth of data from AI Internet of Things, and high-definition media is training terrestrial network capacities. Hydron is expected to offload significant data volumes from ground networks by routing them through space-based optical links. This not only eases congestion, but also ensures more efficient data distribution, especially during peak usage times or in emergency situations. 5. Facilitating space-based edge computing. With the rise of edge computing, there is a growing demand for processing data closer to its source to reduce latency and bandwidth usage. Hydron's contribution would be to enable high-speed inter-satellite communication. Hydron supports the development of a space-based data center. This allows for real-time data processing in orbit, reducing the need to transmit raw data to Earth and accelerating decision-making processes. Hydron is designed to integrate with them, creating a cohesive global communication infrastructure. Lasers in space and stuff are really cool, and they're not without tricky bits. So here is what engineers are actually up against. So the challenges that arise when it comes to a project like Hydron are here. Number one would be to get the beam exactly where it needs to go. These satellites are zipping through space, and the laser has to hit a tiny target that is moving just as fast, sometimes thousands of kilometers away. That means you need insanely precise aiming. We are talking sub-microradian accuracy. Basically, it's like threading a needle from across a football field while both hands are shaking. Number two would be when weather messes things up. Lasers don't love clouds, rain, or atmospheric turbulence. So when you're sending a beam down to Earth, anything less than a clear sky can garble the signal. The fix? Well, use a bunch of optical ground stations in different places and smart software to predict when the skies are clear. Lasers do not go around corners. Unlike radio waves, which can bounce around a bit, laser beams are strictly line of sight. So if something is in the way, even another satellite, you really have a problem. The network has to constantly hand off connections and plan around obstacles in real time. Number four is that space is harsh. It is boiling hot in sunlight and freezing in the shadows. Plus, there is radiation flying around everywhere. The laser equipment on these satellites have to keep working perfectly despite all of that. Number five would be the expense. The tech is getting better, but it's not as plug and play as radio systems yet. Building space lasers that too reliably is extremely complicated, and it's very expensive at this stage. So let me explain the challenges in a bit more detail here. Pointing, acquisition, and tracking. The primary challenge is that the optical links require precise beam alignment between satellites and ground stations. Unlike radio waves, laser beams are narrow and unforgiving. Even a microdegree misalignment can break the connection, and in a moving constellation, the PAT, which is pointing, acquisition, and tracking system, must be continuous and dynamic. So what are the solution strategies here? Number one would be to use fine beam steering systems. Hydron's terminals should incorporate microelectromechanical systems, MEMS, or fast steering mirrors that constantly adjust beam angles to maintain lock, even at orbital speeds. Number two would be to use closed-loop PAT algorithms. These rely on feedback sensors such as beacon lasers and retroreflectors that help both endpoints triangulate each other and lock on quickly. Hybrid tracking with RF assistance. While long-term vision is all optical and the interim stages may use radio beacons to help with initial lock, especially under degraded visibility. The atmospheric interface. The challenge with the atmosphere in space is that laser beams are impacted by cloud cover, rain, dust, and especially atmospheric turbulence, which causes beam wander, scintillation, and power loss during ground-to-space transmissions. What are the solution strategies? The first solution strategy would be that ground stations use real-time wavefront correction systems that shape incoming and outgoing beams to compensate for atmospheric distortion. And the second thing would be to choose the right wavelength selection. Near infrared windows, which is around 1550 nanometer, are used because they experience lower atmospheric attenuation and are eye safe, allowing for high power transmission. Multiple optical ground stations across the globe ensure that if one site experiences bad weather, another can take over. Therefore, this needs to be coordinated through a ground control network. This way, Hydron's links can maintain around 99.99% uptime, even with variable weather, in using real-time switching and global diversity. Number 3 would be the line of sight limitation challenge. The links need direct visual paths, and that's easy between geosatellites. But in fast-moving LEO constellations, lower Earth orbit constellations, maintaining continuous line of sight is logistical and orbital mechanics challenge. So what are the solution strategies here? Hydron includes terminals that connect satellites to each other in orbit, maintaining data flow without always relying on ground stations. Nodes are dynamically aligned and the data can hop between multiple satellites before reaching a downlink station, maintaining service even when LOS line of sight is temporarily lost with the destination. ESA is developing onboard payloads with photonic switching to intelligently reroute data in space, just like routers in terrestrial routers. Thermal and radiation tolerance challenge. Space is extremely harsh, and I cannot say it enough. Extreme thermal cycles, radiation from the sun, and then Van Allen belts and micrometeorite impacts, they are all a threat to the delicate optical components. What are the solution strategies? Well, the optical terminals use radiation-hardened semiconductors, thermal shielding, and actively cooled components. Dual lens or dual laser setups allow a terminal to continue functioning even if one channel fails. Projects like ESA's Skylight and precursor missions have tested components over long orbital durations to ensure Hydron's hardware can last through 5 to 10-year lifespans. Cost and maturity of optical technology. Historically, optical satellite terminals have been expensive, heavy, and bespoke, not suited for scalable networks like Hydron and OnVisions. The solution strategies for them is that Thales Alenia Space working in ESA is developing LEO-compatible optical terminals with modular designs that can be adapted for different orbits and satellite platforms. ESA is leveraging programs like Skylight and ARTES to co-fund the technology development and industrial scale-up, accelerating technology readiness level very, very much. As demand grows for LEO satellite networks and data center interconnects, economies of scale are reducing per unit cost for optical payloads. Result: what was once a niche experimental tech is becoming industrialized, unlocking terabit-scale optical backbones that rival undersea cables. Hydron's solution isn't isolated technical hacks. They are part of a system of systems approach that combines space-based laser links, ground-based optical station, AI-based traffic management, multi-orbit interoperability, and deep integration with terrestrial fiber. It's not just a better satellite link, it's the architecture of a new global backbone. ESA's Hydron project is indeed developing a new satellite platform specifically designed for its ambitious all-optical multi-orbit communication network. This approach is necessary to meet the project's unique requirements such as terabit per second throughput and seamless integration across low Earth orbit, medium Earth orbit, and geostationary orbit. For instance, under the Hydron demonstration system, Hydron DS, ESA has contracted Thales Alenia Space to develop Element 2, which includes a satellite collector in LEO equipped with advanced laser communication terminals. This satellite will serve as a key relay point, receiving data from other satellites and transmitting it either to ground stations or to satellites in higher orbits. Similarly, Element 1 involves a ring of 10 LEO satellites developed in partnership with Kepler Communications. These satellites are designed to create a comprehensive space communications infrastructure, linking satellites in various orbits with ground stations using laser technology. While new satellite platforms are being developed, Hydron also leverages existing technologies and expertise. For example, the project builds upon the European Data Relay System, EDRS, which utilizes optical communication links between GEO satellites and ground stations. Additionally, companies like Mynaric are contributing their advanced optical communication terminals to the Hydron project. This hybrid approach allows ESA to accelerate development by incorporating proven technologies while also pushing the boundaries with a new satellite design tailored to Hydron's specific needs. Hydron's ambition, a fully optical RF free space internet, demands capabilities not yet standard in today's satellite constellation, but fine-tuning existing. However, Hydron is not starting from zero. ESA and industry partners already have Skylight heritage, ESA's optical communication R&D program, EDRS, Space Data Highway, operational geo-optical relay nodes, partnerships with Airbus, Tessat, and others who build laser communication terminals. So in early phases or pathfinders, ESA might actually modify existing satellite platforms, especially for GEO and MEO test relays. They might reuse flight-proven optical terminals with upgrades, and they should also leverage shared satellite buses for rideshare or hosted payload missions. Hydron isn't just about hardware, it's a system-level architectural shift. ESA needs both new designs for critical tech validation, and then they have to adapt existing platforms for cost control and risk reduction. The European Space Agency's Hydron High Throughput Optical Network project envisions a transformative all-optical communication network in space, effectively extending terrestrial fiber optic infrastructure into optic. This fiber in the sky aims to deliver terabit per second data rates, ensuring seamless, secure, and low latency connectivity across low Earth orbit, medium Earth orbit, and geostationary orbit satellites. System architecture overview. Well, Hydron's architecture is structured around three primary components. Number one would be space segment. LEO satellites. They form a ring constellation. These satellites are equipped with optical inter-satellite links, OISLs they're called, and they onboard packet switching capabilities. MEO-GEO satellites serve as relay nodes. They facilitate data transmission between LEO satellites and ground stations. Number two would be ground segment. So optical ground stations, OGSs, are stations that establish high-speed optical links with satellites, integrating the space network with terrestrial fiber infrastructure. And network operation centers are responsible for managing network resources, routing, and ensuring quality of service. Number three is control and management. Network management systems oversee the dynamic allocation of bandwidth, link scheduling, and fault management. Protocol stack implements standardized communication protocols to ensure interoperability and efficient data handling. The key technologies and features of Hydron system architecture would be, first of all, to have optical inter-satellite links, OISLs, optical ground-to-satellite links, OGSLs, onboard optical switching, which are satellites that are equipped with optical cross connections, and they add or drop multi-flip multiplexers, allowing dynamic routing of data without electronic conversion. And then you have WDM, which enhances data throughput by transmitting multiple signals simultaneously over different wavelengths. And then finally, ESA specification for terabit per second optical links. It's called ESTOL. It provides standardized guidelines for high system optical communication. All this talk was to lead towards the capital equipment that will be our topic for this series of Think, Build, Scale. This episode so far has showed you all about how an organization thinks, especially a space organization, how it thinks and accumulates information to finally come up with a new satellite or a new system architecture for a whole new satellite system. So being true to the essence of my podcast, the first episode of the series, which is this episode, we are going to talk about HCIOS, which is Hydron Class Optical Interconnect Satellite. For the sake of knowledge sharing and discussion, this is a completely hypothetical product, and any resemblance to a real satellite is only a measure of my experience in the world of capital equipment. This conceptualized and hypothetical satellite contains 9 major subsystems. Optical communication subsystem, which enables high throughput all optical data transmission between satellites and ground stations, including laser links. Power subsystem, which generates, stores, and distributes electrical power from solar arrays to support all onboard operations. Onboard data processing and control, which manages autonomous routing, system coordination, and real-time data handling using AI-assisted processors. Attitude determination and control subsystem, ADCS, which maintains precise satellite orientation for accurate optical beam pointing and optical adjustments. Security and cryptography subsystem, which protects sensitive data through encryption, secure key storage, and optional quantum key distribution. RF backup and housekeeping communication subsystem provides backup telemetry and command communication via traditional radio frequencies. Thermal management subsystem regulates the spacecraft's temperature to ensure optimal performance of optical and electronic components. Propulsion subsystem controls the orbital maneuvers, station keeping, and end-of-life disposal via onboard thrusters. Look here. Just like any other company out there, ESA will also, first of all, make a business case to show their own. The board will make a business case on how the optical satellite infrastructure creates value for the European government, because ESA, after all, works for the European Union. And as a whole, all of the member nations of European Union have to benefit from HCIOS and Hydron as a project. So what is their business case? Let's check that out. The first is to look at strategic autonomy and data sovereignty. So the revenue driver would be mandatory usage by European HPC centers, AI labs, defense units, and regulated sectors like healthcare, banking, etc. for EU-compliant data transfer. And then you have that EU law mandates, which is sensitive or high-volume data stays within Europe. So Hydron becomes the trusted route for transnational digital services. Just like how Galileo offers a sovereign alternative to GPS, Hydron offers a secure cloud-to-cloud bridge free from non-EU surveillance or jurisdiction. And how will they earn the revenue? That's through government contracts and usage-based licensing for secure routing. Think of it like this. Just as Galileo gave the EU its own GPS, Hydron is giving EU its private ultra-secure internet in space, ideal for sensitive sectors like AI, defense, banking, and healthcare. EU laws will likely mandate its use, which means steady revenue through government deals and usage fees. Basically, it's about keeping Europe's digital sovereignty intact and profitable. If you look at the second reason for the second business case for HCIOS, is the commercial backbone for the space economy. So Hydron's vision is to build a space-based high-throughput optical mesh One major use case of such a mesh would logically be accelerating the distribution of large data like AI models, Earth observation imagery, financial data streams, etc. On Earth, this is actually the role of a content delivery network CDN. So applying this concept into orbit without ESA using that specific term yet, I would really assume that this is a natural and valuable extrapolation for strategy, storytelling, and business models. So with a space CDN system, that's just something I would like to say, I would like to call it. Satellites act as a data cache center, routers and high-speed links floating above the Earth, delivering data faster globally and securely by using optical laser links instead of undersea cables or ground fiber. Imagine a climate AI model predicting wildfire spread. Instead of waiting 6 to 12 hours for satellite images to be downloaded and processed through ground fiber, the space CDN instantly streams fresh infrared imagery across satellites to regional AI models running in cloud centers, updating predictions within minutes. In finance, defense, self-driving cars, or disaster response, this instant satellite to model capacity is absolutely priceless. I really hope ESA pulls it through. I really hope they make it happen. All right. The AI infrastructure and digital twin support. This part of the slide focuses, or this part of the business case focuses on a key revenue opportunity for the Hydron satellites by supporting AI infrastructure and digital twins. Digital twins are nothing but virtual replicas of real-world systems like smart cities, farms, supply chains, even defense operations. They need a constant real-time feed of data from satellite sensors and AI models. Imagine merging weather satellite data with wildfire alerts and logistics tracking, all happening in real time to help governments or companies that would need to react instantly. AI will finally be used as a service, and then companies would rent out model training and inference services. Hydron would let them move massive models, GPT-sized models, or climate simulations across borders quickly and securely. So where's the money in all of this? The government or ESA or EU programs could sell premium bandwidth to cloud providers or AI service platforms. They could bundle Hydron into other EU-funded initiatives, and then they could charge for reliable integration into institutions and national infrastructure. Basically, Hydron becomes the invisible plumbing behind Europe's AI power grid. And yes, people pay good money for high-speed, secure, dependable plumbing. What's the big idea here? Hydron, this space-based optical network, doesn't have to be government-run only. In fact, one of the best ways to turn it into a revenue engine is to let private companies plug into it. Think of this just like telecom giants lease undersea cables and fiber routes today. Hydron becomes the orbital version of that, a satellite fast lane in space. Who are the partners? Well, there could be three major big groups that ESA can partner up with: European cloud companies, global cloud giants like Google Cloud, etc., and then telecoms. So European cloud companies like OVH Cloud or Scaleway, they want high-speed EU-compliant infrastructure and will happily pay to move data securely across Europe or beyond. Global cloud giants like AWS, Google Cloud, etc., especially their EU divisions, which they would need to meet European data laws. So if they can route sensitive or real-time data through Hydron instead of US-owned cables, that's really a win. Telecoms like Deutsche Telekom and Orange, they can integrate Hydron routes into their own network. Think, data goes into fiber, then goes into satellite, then fiber creates hybrid Earth-space paths. So how does ESA make money through all of this? ESA does not need to be the end provider. They can co-brand services. They can charge for access to orbital routes, and they can license premium features like latency guarantees, encryption, priority bandwidth, etc. So Hydron becomes the space layer underneath cloud, AI, and telco services, just like today's invisible but essential undersea cable network. Cleaner, faster, and sovereign. Why defense and civil protection will actually pay for Hydron, you think? So governments care about security, speed, interdependence when it comes to communication. Right now, a lot of that traffic flows through vulnerable, congested, or foreign controlled infrastructure, especially radio frequency RF systems that can be jammed or intercepted. Hydron offers something way more secure, a laser free, RF free satellite communication, meaning no jamming, no eavesdropping, and no signal pollution ever. Who needs this? Well, European defense and intelligence agencies, they need it. They need it for coordinating missions, updating military AI models, or securely sharing sensitive surveillance data. Intelligence, surveillance, and reconnaissance, emergency services, and disaster response, like during wildfires, flood, or earthquakes when ground networks are down or overwhelmed. NATO-aligned operations. This gives Europe the option to contribute secure communication layers without depending on US assets. And how does this actually make money? Governments already spend billions on secure communication infrastructure. ESA can tap into that by charging national defense budgets for using Hydron's secure optical channels, setting up intergovernmental contracts for rapid deployment scenarios. Example, encrypted links between EU capitals during crisis coordination. In a nutshell, Hydron gives Europe its own digital fortress in space, and defense ministries will actually absolutely pay for access to that. So what's the long-term payoff? Well, Hydron will actually generate money for Europe year after year, not just as a cool science project, but as a sustainable digital infrastructure. Where does the revenue come from? Secure data routing, bandwidth leasing, strategic cloud partnerships, defense contracts, and IP licensing and innovation, as we discussed earlier. Spinouts and SMEs, they will also be using ESA's tech pipeline pay for licensing or return value through innovation partnerships. So with this, and so this is all for episode 1 of our satellites series. I'll see you guys in the next episode where we are actually building a satellite called HCIOS for ESA's Hydron project. See you there.